Well, I'd like to welcome the second speaker, Professor Graham Cooks from Purdue University, and he's going to talk about miniature mass spectrometer systems with spectrometry systems with external ionization and also ambient ionization method.
Could you move the microphone closer to the speaker so we can hear better?
So I want to say thank you very much to Jung-Ho Yang for organizing the session, which he did, even though my name was on it. And thank you for your patience in trying this experiment with us of walking back and looking at the mass spectrometers and trying something a little different at Pittcon. So this talk is very similar in many ways to David's talk, but it also contrasts in some ways. So it's also about ion traps, it's about tandem mass spectrometry, it's about trace analysis, but it's external rather than internal ionization. And we concentrate on being able to look at extremely badly, perhaps, small amounts of non-volatile molecules in very complex matrices. So you could call this barely adequate mass spectrometry, and that's our objective, just to do well enough to solve what turn out in many cases to be important problems. There's a number of authors. There's myself and there's Yang, and then Lin Fan Li and Ren are the people who are going to do the demos. Paul Hendricks is back working on miniature mass spectrometers, and a number of other people who have worked with us in this project, which actually stretches over a very long period of time. I acknowledge support of both foundations and government agencies. So the key to miniature mass spectrometry, I believe, can be found in addressing these kinds of questions on the right, and the particular solutions that we've adopted are on the left. And so firstly, one needs to be able to operate, if at all possible, at pressures which are closer to atmosphere than the conventional range in mass spectrometry. And if you can get it at atmosphere, then so much the better. If you can do mass analysis at atmosphere, then good for you. If you can't, as we do, we'll be down at 10 to the minus 1 to 10 to the minus 2 torr. And the kind of device that allows you to do that is a quadrupole ion trap in some configuration. The next thing we would like to do is to have a small device, a small analyzer, and we just saw an instrument which had a 2 millimeter internal radius in a cylindrical ion trap. And so that's a shrinking of a factor of 5 from the original conventional benchtop instruments, and it's obviously a move in the right direction. So we too have been working with miniature ion traps, including miniature cylindrical traps over some period of time. What I'll show you, though, are rectilinear ion traps, which is also a simple geometry, easy to manufacture, but which can also be easily miniaturized. There is an advantage if you want a volume in which you can trap ions if you use an array, and arrays can be made up of cylinders, and they can be made up of rectangles. They are made up in a variety of ways. The advantage of an array is that you can use smaller individual devices, lower voltages, and yet get comparable ion trapping capacity, and you have to balance how far you're going to go with the array if you want to maintain good resolution. So quadrupole ion traps, mini traps, arrays of traps. If you're going to aim, as we do, at doing mass spectrometry in the field, in the real world, then you most definitely will be wanting to do tandem mass spec, because that allows you to characterize individual compounds in a complex matrix. And so we implement that in ion traps particularly readily. Of course, you could have 2 stages of some other kind of mass analyzer, but it's easily implemented, and so that's what we do. And so I'll show you MS, in fact, I think MS to the 6th in these small little devices. And then importantly, if you're going to seek to do materials which are condensed phase, solids, non-volatiles, out in the ordinary open air, then you will want to do some form of ambient ionization, and you will then have the problem of transferring the ions into the mass analyzer. This avoids some difficulties and creates others. It avoids difficulties of contaminating mass spectrometers. It creates the difficulty of separating ions from the atmosphere in which the ions were created. And I'll show you how we do that. It's a stealth technology. It's one that we've tried to beat ourselves and we haven't been able to. It's transfer from the ambient environment discontinuously. We call it DAPI, discontinuous atmospheric pressure interface. And then finally, and importantly, because this has not been sufficiently recognized, it isn't really the size of the analyzer that counts. Fundamentally, it's the size of the system. And so you need to miniaturize the entire system. And when you do that, you'll have a device which can be carried around in the field, in the clinic, almost anywhere, and bring the advantages of mass spectrometry, which are very well known, to the portable area. So briefly looking at each of these properties, and my talk is very, very short so that we have quite a lot of time to look at the instrument later on. Cylindrical ion traps, this could just as well have been rectilinear, but I pulled this out because there's a mass equation, mass here, potential, and the size of the device, and most importantly, the power shrinks as you shrink the individual elements. So quadrupole ion traps in one form or another are a really, really good way to start to do walk-around mass spectrometry. The miniaturization is relatively easy. This is a diagram that comes from a long time back, 1989. This subject has been in some preliminary form or another for a long time. This was a 3.5 millimeter ion trap which was manufactured. Talk about turning swords into plowshares at the Los Alamos National Lab using some machinery that was normally used to create components for nuclear weapons. And the hyperbolic shape of a conventional pole trap, this is not cylindric, the one that we did in this paper wasn't cylindrical. This one that's pictured is, but this one was hyperbolic. 2.5 millimeter radius pole trap. So we mentioned arrays. That's the other thing we want, and a collection of arrays of different types, different geometries. This one, rectilinear geometry, so one long dimension, and they're arranged like this so that you can generate ions, pass them around in this direction, but more conventionally, just use them to eject ions to a central electron multiplier, which is in the middle of that set of arrays. What we're showing at the back of the room is going to be a single rectilinear ion trap. It won't be an array in spite of the advantages of arrays. So if arrays are good, then you may want to miniaturize a great deal more, and you may want to have arrays of micro-generated cylindrical ion traps. And I put this up for Dan because Dan Austin was involved in this project from a few years ago, working with Sandia, creating these 1 micron internal radius individual cylindrical ion traps, of which there were 1 million on a chip. So just an example of the fact that you can go too far. This slide and the next are the two key slides, perhaps, to do the kinds of things that we want to do, which is biological mostly, but also environmental and clinical and so on. We want to use ambient ionization methods for multiple reasons. So ambient ionization means that you make ions without working up your sample, so that's one good reason. No extraction, no pre-concentration, none of those things. And you make those ions out in the ambient environment. And so here's two methods, one of which you may be familiar with, which is this paper spray experiment, which doesn't, in fact, require any chemicals. This is just water, and it's just condensation. Certainly in Texas in the summertime, it just falls down on everything. So there's a sample on the paper, and solvent is being applied, a drop of solvent, the potential is applied, and you get microdroplets which are released from the paper and which carry analyte that was placed on the paper to a mass spectrometer, which in the cases we'll look at now will be a miniature mass spectrometer. So there's really not much to that, and there's really even less to this one. This we call touch spray. You touch a metal device to an object. The object, for example, may be a bacterial colony in a Petri dish. And then you do the same over here as we've done over here. You add a drop of solvent, apply potential, and you create little droplets containing microorganisms in this case, or containing some chemical of interest or some biological compound or some protein or whatever. So both of these very, very quick methods of ionization, which are consistent with the speed with which one can take MS and MSMS in quadrupole mass spectrometers. And then the key to doing ambient ionization is, in fact, this discontinuous atmospheric pressure interface, which works on the basis of compression of a tube, plastic tube, and the introduction of ions and gas, air, into the vacuum system periodically. And right over here, the period is on a second-by-second basis. So you introduce the pressure rises. It rises to 1/10 of a torr, and you let it drop a little bit and record the mass spectrum. So that's the DAPI that we need. And when we're finished with all that, this is what we've got. We've got a path away from conventional benchtop mass spectrometers to small devices which can be operated with any of these ambient ionization methods. I talked about that one only, provided you use this discontinuous interface, this atmospheric pressure interface, in order to introduce the ions and the samples into the miniature mass spectrometer. And that then represents an integrated miniaturized mass spectrometry system. And these things have been around for atmospheric ambient ionization since 2009. So time's marching on, and we're not marching at the right rate, I would say. So I'll show you some data that had been taken up to that time and a little bit beyond, just on the one slide. What were we able to do before we got to the current generation of instruments? So this is the Mini 11, the one in the back of the room is Mini 12. So using desorption electrospray ionization, another ambient method on the Mini 11, using negative ions, here's a spectrum which shows a variety of explosives being analyzed directly in a very, very short period of time. Here's an experiment in which we're looking at biological material intact, in fact, in vivo. And this is a leaf spray experiment in which the leaf of the tomato takes the place of the paper, and in which the major peak is the alkaloid, which is doubly charged, in this instance, tamatine. The question about mass range always comes up. It's not a good idea at this stage to use these instruments for proteins, but can be done. So here is cytochrome C going out to molecular weight 12,000. And here's a paper spray experiment showing MSMS on fruit. This is another example on the Mini 11. This is tamoxifen and a labeled compound in whole blood. This is at quite a high level, micrograms per mil, using the 11.5, and that's the instrument, and this is a picture of the instrument. And then turning the page to the next generation, this is Paul Hendricks. These are a couple of his friends. They're wearing mass spectrometers. This is a low-temperature plasma instrument, ionization source, and then the instrumentation on, including a miniature ion trap mass analyzer, which looks like this, exploded view of this little device. It's 4 by 5 millimeters of the characteristic dimensions. The length could be varied. It's 30 millimeters. So I already told you, in terms of mass analysis, the operating pressure, 100 millitorr. And this is cocaine. You may recognize it. molecular ion, protonated cocaine, tandem mass spectrometry. It fragments by collision-induced dissociation. You produce products, and then further fragmentation, and you can certainly provide the necessary specificity. These instruments have both positive and negative ion detection capability, and of course a single analyzer for tandem mass spec. And in a number of cases that I'll show you out of complex mixtures, parts per billion level detection capabilities, as well as quantitative capabilities. So this is a reconfigured instrument. This is Mini 12. It's in a configuration which is suited to doing the paper spray experiments. At the front end has got a cartridge loading system, and then a solvent pump that has to do with paper spray, providing the solvent and the voltage for paper spray, and then the rest of it is a mass spectrometer set up around a rectilinear ion trap and appropriate vacuum system. And as with some of the other systems, of course, you can take data and you can do it in an automatic fashion, and in fact interpret some of the spectra that way. So let's look at some data on this. So we're going straight to data which is hard. So this is whole blood, and this is the drug amitriptyline, and it's going to be measured, and in fact everything that's going to be measured out of blood is done at the MSMS stage or beyond that stage. So this is MSMS using 278 to 233, and then the isotopically labeled compound, which is added in order to allow quantitation. So this is overreaching, isn't it, to try to do quantitation in a miniature mass spectrometer in a few seconds. But if you don't overreach, then you don't get anywhere, so we're overreaching. So we add that and make two measurements. They're reaction monitoring measurements, and this is the one transition. The other one is add 6 units, and you're looking at the isotopically labeled compound. This is the ratio of those two intensities in the MRM, for those that know that, MRM spectrum, and it is linear after you get out beyond about 10 parts per billion, and it runs linear through the therapeutic range, which is this range for this particular drug, and then goes on out linear over at least 2 orders of magnitude. What's even more important is the stuff down here, which has been given question marks by this computer, which is really smart. It's nanograms per mil. This is adding no material, and this is 7.5 nanograms per mil, not a question mark at all, 15, 60, and so on. And the important data is the RSDs. So the reproducibility then is all the way through the therapeutic range, but even below it. But this is the therapeutic range, is less than 10% RSD, and that's what you need to have for a method that's going to see clinical use. Okay, so let's look in the last few slides at some of the other things we can do. We can look at samples in whole blood, as we've already said. We can, you can do blood, then you should be able to do fruit, and you should be able to do water. These have got stars because there'll be demos covering these two experiments. So this is a different drug, verapamil, in blood, and this is done by an extraction spray experiment. So the material is on paper, but it's enclosed, and we spray more efficiently that way. These are the characteristic fragment of verapamil 165. This is the compound you just saw out of whole blood. And thiobendazole on orange peel. So there's no workup in this case. This is just looking at the compound on the surface of the orange. And here's the MSMS spectrum here, starting from 202. This is 202 right there. It's the selected precursor ion. It's been completely dissociated to 175 and 131. And then atrazine in water. This is relatively simple. There's isotopes of chlorine. And its fragmentation. So if you want to go further than multi-stage, Clenbuterol This is the MSMS. Here we've isolated 277, and these are the fragments. 259 is the first fragment. Here we've taken the next step, isolated 259, and fragmented that. It gives 203. Again, the next step, isolate 203. Each of these inserts is intended to show you how clean the isolation is. Isolate 203 and fragment, and you get 168, and then isolate 168. Here it is beautifully isolated. Absolutely nothing wrong with the signal to noise after 5 stages of MSMS. Here are the fragments, nothing wrong with that spectrum either. So you can go through those multiple stages quickly in order to verify the nature of the analyte. Other systems of interest would be looking at compounds which are present as a powder. So forensic applications, for example. So here's verapamil, here's the structure, here's the protonated molecule. And again, we're looking at MSMS because that's where the information is. We've seen cocaine before. This is whole blood, but it's now dried blood, and it's on genes. So this is touch spray experiment. You've got blood on genes. You touch that part, you add a drop of solvent, you hold it in front of the mass spectrometer. This is what you measure. The blood had 10 ppm of cocaine in it, and we're not at the limit of performance in terms of this spectrum. You can see we're going further and further into the netherworld here. So these are latex gloves which have got methamphetamine on, and the same sort of thing. It's direct analysis from that surface and highly characteristic, and it would be very surprising if there weren't a few stray peaks around under these circumstances, with a total of 1 microgram of material on a latex glove. And MDMA on fresh blood, paper spray. So there's a whole variety of spray methods, DESI plus obviously electrospray, if you can use that. Then these other spray methods that I've just introduced you to briefly. So what we'll do now is we'll look at this instrument. This is the Mini 12. It's considerably bigger than the previous instrument that we showed a couple of years ago, the Mini 11. It's meant actually to sit on a desk. This one, it's not much heavier, and it's 65 watt is the average power. If you were to look inside, this is what you would see, starting with the introduction system, the DAPI introduction, the electronics, the vacuum system, and positive negative ion detection, and the key to the whole thing, which is the mass analyzer itself. And so for the purposes of the demo, these are the 3 demos that we'll try and get through. It may be good if people wanted to ask questions before we go back there, Joe.
Yeah, go ahead.
Here, half of auditory, it is IMS specialist, and maybe the same question. What is the difference in sensitivity or assessment, internal ionization mass spectrometer and external mass spectrometer? Do you have some number approximately?
Okay, so the question is the difference in sensitivity between internal and external ionization. And I don't really think there's a number, but I do think it'll favor internal ionization very greatly. So if you have a sample which can be put in a mass spectrometer vacuum system, then by all means go ahead and put it in, because you'll do better in terms of sensitivity that way. But you wouldn't put blood or urine or latex gloves in there. And so you would have to come up with some scheme which involved transferring material, and we prefer not to. We prefer to just transfer the ions rather than transfer the material. But the previous presentation by Dr. After, you already heard how you can release materials thermally and otherwise. So there's 2 ways to skin the cat.
If
you've increased the size of the Mini 12 on the Mini 11, so you haven't miniaturized, you've gone through a minimum and coming back. What is the main reason for that? What's the main gain from going to a weightier instrument?
So the question's about the size of the Mini 11 and the Mini 12. The analyzer, the mass analyzer, is exactly the same. So we've not done anything there. We added material associated with the particular paper spray ionization methodology is the main thing that we added. We're in the process not of coming back, but of doing more weight loss, because one of our projects involves implementing much more rational pumps and a pumping system. So if I promise you I'll lose 2 kilos by next year, is that okay?
That's okay.
Thank you. Okay, you guys ready?
One question. We know about your mass spectrometer about last 5 years at least. We heard about this and we know. Can you tell me approximately when it will be commercially available?
So a couple of flattering comments, and then he asks, when will the instrument be commercially available? Probably never at the rate we're going. Okay, so we only have 5, 7 minutes, 8 minutes. So if you want to come to the back of the room, we're going to go through these in this order. Cocaine in serum, thiabendazole in orange homogenate, and atrazine in water if we get to it.